Lithium, sodium, potassium are reactive metals in group 1 of the periodic table. Sodium metals tarnish in air to form a layer of sodium oxide. That means oxygen reacts with them on its surface. 0.92 grams of sodium combined with 0.32 grams of oxygen in this oxide. Calculate the empirical formula of the sodium oxide. And when they do this, you basically will need two values. You'll need the relative atomic mass, the AR, of the chemical in question, and the real mass, which was worked out experimentally by weighing it. Now, this is for 3 marks. Now, sometimes they will give you the mass of the oxide, that means the metal bonded with oxygen, and the mass of the metal, and you'll have to subtract the two to work out the mass of the oxygen. But here, it's given you the mass of sodium, 0.92 grams, and the mass of oxygen, 0.32 grams, separately, so that's one step you don't have to do. So the first step is work out the number of moles, and you do that by dividing the mass by the AR of that element. So here we have sodium, which is going to be 0.92 mass divided by its AR, which is 23. And that will give you 0.04 moles of sodium. That's how much we're dealing with. Oxygen is a mass of 0.32 grams and an AR of 16, which gives you 0.02 moles. Be aware that you're dividing a very small number by a very big number, and don't be put off by that. That is exactly what you have to do here. You just follow this formula, mass divided by AR. Don't let your brain think, oh, it must be the other way around because this number's bigger. Now you have the number of moles, you have to work out the empirical formula. So you divide both values by the smallest of the two. The empirical formula is simply the simplest ratio of elements in a compound or in a molecule. So you divide both values by the smallest of the two. Luckily here we have a smallest of the two. Sometimes the values may be exactly the same, so you just divide them by, well, it doesn't matter which one. If they're both 0.04, you divide them both by 0.04. But here one is smaller. So you do 0.04 divided by 0.02, which is 2, and 0.02 divided by 0.02, which is 1. So that means for every 2 sodiums, we bond with 1 oxygen. So you must write down the chemical formula. This is the empirical formula. Some students just leave it as the ratio, 2 to 1. No, you must write down this, otherwise you don't get the marks. Next is a balanced symbol equation. So sodium reacts with the water to form sodium hydroxide solution and hydrogen, typical alkali metal water reaction. Complete the balancing of the equation for this reaction and add the state symbols for each substance. Now normally I'd show you how to balance equations, but to make it a lot simpler with alkali metals, it's really easy. You just have to remember that the first 3 chemicals in the equation just have a 2 by them. 2 sodium react with 2 water, react with 2 sodium hydroxide. It doesn't matter what this is. If it's not sodium, it'd be lithium, so it'd be lithium and lithium hydroxide, potassium and potassium hydroxide. It'll still be 2, 2, 2, not on the last one. Next, it's state symbols, so that is whether it's a solid, liquid, gas or aqueous. So obviously a big lump of metal is going to be a solid, or a small lump of metal, just metal will be a solid. Water is a liquid. Sodium hydroxide is basically dissolved in the water. It's a dissolved chemical, so that would be aqueous, and hydrogen would be a gas. This is a really good example for state symbols because you get one of each type, solid, liquid, gas, aqueous. So that's why it's quite popular. In an experiment, equal-sized pieces of lithium, sodium and potassium are added to separate samples of water. A flame is produced only with potassium because, what's the most logical answer? Potassium is the softest? No. Lowest melting point? No. Is the only flammable metal? No. Actually, sodium can also ignite, but it is the most reactive. That's why it ignites. It produces the most gas per second, and it's hot, and it ignites the gas. Explain, in terms of electronic configurations, the increase in reactivity from lithium to sodium to potassium. Now this is an odd question because I've seen this being reduced from a 6 mark to a 4 mark, and now it's a 2 mark question, and it's quite hard to put all that information to 2 marks. Well, the electron configuration tells you that they all have 1 electron on their outer shell, 1, 1, 1, and therefore they'll need to, or they will, lose that electron or transfer that electron when they react. Now you can see as you go down the group, there are also more shells. The electron configuration tells you how many shells, 2 shells here, 3 shells here, 4 shells here. Now, the more shells an atom has, the further that negatively charged electron is from that positively charged nucleus in the middle of the atom, which is attracting the electron to that atom. So you can see the more shells, the greater the distance, and the weaker that force of attraction is. So here it's even weaker because there's a bigger distance. That means it's easier for it to lose that outer electron. So there's a lot of information here. How do we get it in 2 marks? Well, firstly, the distance between the outer electron and nucleus increases. We can see that. That's a really important point. And secondly, so the outer electron more easily lost. That's what we're saying. So it's easier to lose it. I think what's a bit unfair about this question is the use of electronic configurations. So you might think you have to talk about 2.1, 2.8.1, when actually it's using that knowledge. What do you know about these? So it's a bit of a misleading question. But you can always fall back on answering it without thinking about this, because it says just why they're becoming more reactive down the group.